Hello everyone, welcome to the channel. Today we'll be understanding how Claude Code works. Like Claude Code is one of the best examples of uh, harness engineering agents. So we'll understand how it works in simpler terms with some examples. And these architectures, uh, we work with them daily. Let's understand how it works. So, uh, let's understand few of the key points that we already know, like the models. What are the models? Claude has something Fable, maybe Opus, maybe Sonnet, maybe Haiku. They are the one that will give us all the knowledge. They have the intelligence. That's the intelligence layer. But so does other companies. They're good models. But what makes Cloud Code stand out from others is because the whole ecosystem they have built around the model. That is the harness engineered agent, or you can call it a loop, that allows Cloud Code to perform long hour tasks, complex tasks. Tasks when we ask, do this, then verify this, then update the document, then let me know. Cloud can delegate tasks which other ecosystem are not doing perfectly right now. That's why Cloud Code is one of the superior products as compared to other competitors in market we have. So let's take one example of how, like, we have a bug and we want the, like, we have a bug, we got the screenshot and we want Cloud Code to fix it, then update the documentation. It's one of our daily to daily tasks. So how we'll do it? So we open Cloud Code and type. Uh, let's start with opening Cloud Code. Okay. So we open a repository or maybe a directory and type Claude. Then what is the first thing that Claude asks? Are you allowing to use this space for Claude, or are you trusting this with Claude? So that becomes the execution environment. In production, that becomes something like Docker or something else, but in local, that directory, that machine's particular directory where we initiated Claude and we gave permission to that, that became the execution environment. That is a point five. We'll come to this one by one. Then, if you have observed something, by default, a Claude.md, or for other models, other vendors, it becomes agent.md. That is created whenever we do this Claude. So that becomes this instruction, how the Claude, like the Claude code, is going to behave in that execution environment. Or in simpler terms, that becomes workspace. If you might have noticed, Claude creates workspace when we give permission. So how the agent is going to behave in that workspace gets defined in these instructions. Now we have a screenshot and we are trying to fix the bug. So what we do? Hey Claude, at the rate, here is the image, or at the rate. You remember, no? We use this at the rate symbol, or maybe we put a screenshot. So that becomes the context delivery. We put the context. Then that context goes to model. But with time, we put a lot of data, a lot of input. Don't do this, do that, do that, do that. Here is the file, here is the whole repo, here is the screenshot, here is the video. We put a lot of data. So it becomes difficult for model to manage the knowledge there. That's a classic problem. So how Claude does solve that? It uses a context management layer. So this li- like this layer is whole for the context management. So we give lot of data to Claude in prompt or in text. What Claude does there is to it's an RAG of its own, retrieval augmented generation. So it creates context, retrieve them, rank them, then when the window reaches, it compacts them, like some sort of summary. It summarizes them. So we save a lot of bandwidth there. Like if our bug is related to SQL, something related to SQL, when we get given an instruction, that will be ranked higher than something related to other bug that we given or other files that we give. So that becomes the context management layer. Now model has the instruction, environment, and context. So we have given the error is in this screenshot. Have a look at it and fix it. So now what will Claude do? Claude will try to invoke some tools. So tools can be something as complex as like mm, a own sub agent. Like agent is a tool. That's possible also. Or as simple as a simple Linux command like cat, make directory, nano. This can be also tools. Or simple like anything that will take an input, give an output from agent or from model, that becomes a tool for us in this layer. Then, suppose now what are we capable of? We have a problem, we have a proof, and we have tools that can verify that this problem where it exists. But now we don't have any layer to fix the problem. We don't know what to like. We know model knows it is intelligent. It knows what needs to be done, but it can't perform action. For that, we got tool. But we, as human, don't allow models to perform action always on it. So that becomes another layer, like the orchestration layer, where the model will ask us for the permission. This is where Claude asks, are you allowed to do this task? We say yes or yes, approve always in this, uh, approve always this command in this repository or no. And these days it has become more advanced, like we can chat with it. Like we can directly say, don't do this, do that. That becomes an orchestration layer where tools can be called. See, tools and model. These combinations, although model is intelligence, tools can be poison. Tools can be a Git repos page. Tools can be a web report. Tools can be anything, and that can have wrong data. Even if with the correct parameter, tools can return messy data, data that is not correctly parsed, data that is outdated, data that is wrong. So that comes the orchestration layer, where we can retry, where we can verify, where we can approve that do this, do that, don't do this. So that becomes the orchestration layer. Then comes the sub-agent. So it like these days you can invoke Claude sub-agent by saying, "Hey Claude, create a team of specialized sub-agents or normal sub-agents, and using that solve this problem." So in this seventh step, Claude will create multiple sub-agents. Or if the task is very simple, no sub-agent is required, then you don't need sub-agent at all for that. But if you are doing some complex task, you may have seen Claude asking you uh, at the end, it will ask two options. Do you want sub-agent driven development or inline development? So that is this layer, sub-agent driven development. What it gives us is, see, we have 15 tasks to do, and if we do all that like serially, it will take a lot of time. It will bring in a lot of context that will give LLM a good chance to hallucinate, and the context management and tanking. We need to do that. That becomes a problem. That becomes a pain. So we delegate the task to sub-agents. That becomes a loop of its own. And we can do that in parallel. We can save time. We can retrieve the task. Like suppose uh, we have three agents. One agent is doing uh, code change. Another agent has the task to make a build after the code changes. And third agent is parallelly making the updated documentation for the successful build. But in the second agent, who is supposed to make the build, is failed. So we don't need to do the third agent as the second is already failed. So we can stop that in midway by the sub agent. Whereas in serial execution, we have to wait for all the agents, like to verify. Then only we can pause that. But now we know the error is there, we pause that. So this keeps up the context management along with time saving, along with um, each task becomes a loop of itself. So it can correct itself, again ask your approval from orchestration layer, then fix it. Now what have we got? We had a problem, we had a proof, we have intelligence, and we have a solution, and we made that. But how can we trust that? Like, agent tells us that, yeah, I fixed it, it worked. But how will it test it? We can simply agree that, and believe. Like, mm, then comes the verification layer. If you remember, like a few months ago, when we asked agent to do research work, it used to add own made up links for papers, own made up YouTube video URLs, own made up website URLs, own made up paper links. So that's the problem. So now with harness engineering, we can verify that. How will we verify that? Again, we have models intelligence. We know what to verify because of this verification layer. Now comes part into skills and procedures. So let's talk about skills. Suppose we are working on something related to Hugging Face. Hugging Face is open source, whole like holistic AI and ML open space. So we are working with Hugging Face, and we want our agent, like Claude Code, to deploy our code in Hugging Face. Now we have written the code, we've verified it, it's working. Like we verified all the syntax. By verification, we mean all the syntax and all. So it's working. Now we need to deploy and push it to the Hugging Face data hub or project hub. Hugging Face space we call it. We need to push that. So if you remember, companies these days, like Hugging Face, like um, LLM observability companies, these companies, they are giving us agent skills in their website. So we can integrate them directly. Maybe we call them plugins. So we add that. Now, this verification layer knows what needs to be verified. What is the procedure? What is the latest procedure? It just doesn't need to go to web search for Hugging Face deployment process 2026 July. Because Hugging Face has it's their duty to keep the skills updated, up to date. So now we can verify the task. But we verified. But what if we repeat the same mistakes again and again? So that becomes a skill of our own. Like, people are selling skills.md these days. So that becomes our own workspace skill so that we don't need to do the same prompting again and again and again. So we do that. In this whole process, we are feeding LLM, the Claude Code, lot of data from our side, from the code side, from the documentation, from the proofs, and a lot of feed. So what if the LLM crashes? So what if like the model API call fails. So then it might happen that all knowledge, all conversations are lost. So there comes this durable state, like it's memory layer. Think of it as simple as a simple SQLite file to complex something like time series database. It tracks everything, whatever we tell to model, which file it opened when, what was the output of running this command, what was the thing we told it to memorize. Nowadays, we can tell Claude to memorize this. Like example, always keep in mind that never add co-authored by Claude Code in GitHub push. So it remembers that. That's the durable state. Even if it crashes, it saves to at some point where you don't need to start the whole start from beginning. That becomes maybe your planning.md, plan.md, markdown files where we plan and where we do a checkbox that this is done, this need to be uh, verified. So this durable state, it keeps track of everything. Then we've done verification. We know it works. But suppose the verification failed. So we can't see the logs or durable state is not up to date in that point. So there we need this observability. Like it is the whole think of like the whole open logs, but whatever we are running, whatever we are. So here we can see why it failed. Oh, there was a special character here, so it failed. Code related things, it's easy to verify. But something like research related things where LLM is making false like URLs. So we verified that. And in the observability, we will see that here the verification failed or LLM is saying like the whole Claude agent is saying something wrong. So where we can detect that? We can detect that in the observability layer and make a ground rule for it, or maybe a red teaming for it, maybe so something for it. Then put that into the observability layer and put that in either skills or procedures, or maybe in the durable memory, maybe in the instruction. So it won't repeat the same mistakes again. So now it was the whole overview. Now let's take into a simple example. I have a screenshot, there is a bug. I'm asking Claude Code to fix. So instruction is by default created and it gets updated. So I attached the screenshot that becomes a context element. Then it went to the model. Model saw the screenshot, found the text, found the context, retrieve it, ranked it, and on requirement it can compare. So it knows what is the issue. Now the model goes to the file and reads that file, find that part of code, and analyzes that. That becomes this tool interface in the execution environment. Now it asks for us to allow to edit that file. That becomes the orchestration layer. Now it has a plan and it asks, do you want agent driven development or inline execution? So I said agent driven development. Now that task, agent, from the orchestration layer, we skipped a little bit. From the orchestration layer, everything always is shared between the durable memory. So nothing gets left behind, and we are up to every part of the whole harness system is up to date with the memory, latest thing, what happened. It's not like one agent is doing something, whereas like the model itself has verified that this thing won't work in the durable state memory. Durable state memory is always up to date. So then using the durable state memory by every component, agent fix the thing. Now the verification happens and we check in observability. There is no edge cases, no issues. Then, depending on our requirement, we may add skill, may not add skill, or simply we are doing some third-party integration or updates. Okay? Skills are used by the agent itself. So this is all how I understand the agent harness system. Again, I'm not an expert, but I work as an AI engineer and I would love to share my learnings. And if there is any mistake, please feel free to point me out. Thank you. Have a great day.